Okay, so we're going to go ahead and wrap up the last 7 or 8 slides from the second set of chapter 3 and 4 slides. We're going to revisit acid-base titration and see some of the math that could go along with this. This slide is kind of showing you two different parts of what we were doing. So if you kind of look on the left half of this, it's talking about the calculations we were doing before. So what we're looking at here, going between grams and moles, and so we can kind of follow this flowchart, grams and moles of reactants and products. These are kind of the things we were thinking about with our theoretical yield type problems. And now on the other side here, we're kind of thinking about doing the same sort of calculations but with molarity. And I'm going to write acid-base titration over here because that's really the one and only example that we're going to do now. But in theory, there's other calculations you could do considering volumes in terms of chemical reactions. That's really all we're concerned with at this time, though. So we were talking about acid-base neutralization before, but we can also talk about acid-base titration, and effectively those are the same thing. So in this setup, essentially, you have an acid solution in a beaker down below. Then you have a solution of base in our burette. And the burette, basically, you can very accurately add a certain amount of liquid from it. So in this typical titration setup, we're adding base to the acid, and our goal is to add the correct amount of base to completely neutralize the acid. And so normally in an acid-base titration, we could either use a pH meter, so it would accurately track the pH as we add base to the acid, or we can use an indicator. And so a very common indicator is a molecule called phenolphthalein, and phenolphthalein, it's going to turn pink at a pH just slightly above 8. So normally we're starting with acid, which is low pH, and we're adding base, which will increase the pH, and we keep adding base until we just get a faint pink color to tell us we've just added enough base to neutralize the acid. Neutral pH is 7, so right when we get that faint pink color to show up, then we know we've added enough base to neutralize the acid. So for our purposes, whenever you see titration, we should use that in the same way that we use neutralization. It's not exactly the same, right? Titration, you could keep going beyond the neutralization point, but we're going to use that terminology interchangeably. So the concept that we want to have in mind as we approach this is the purpose of neutralization is to reach a point where whatever the other reaction conditions are, that the moles of base we add equal the moles of acid we initially had. And that's the typical way that we're going to do it with acid in the flask down below and base in the burette, but you could also do it the opposite way as well. It's just depending what you know and what you're trying to figure out. So this is an old slide we saw earlier in the chapter, and here's our molecular equation describing the reaction between an acid and a base, and even more specifically a strong acid and a strong base, meaning they dissociate completely. So here's the ionic equation with things already getting crossed out, the spectator ions. And then if you remember, that gets us to our net ionic equation, where we really can talk about the most important aspect of our acid-base reaction, which is simply just H plus being generated from the acid reacting with hydroxide generated from sodium hydroxide, and ultimately they react together to form water. So again, neutralization and titration I'm using interchangeably, but this is the intent that again, we can say the same thing, moles of acid, meaning H plus, equals moles of base, meaning OH minus. So that's our intention when we talk about these reactions. And again, we're focusing on when we're reacting strong acid with strong base. Okay, so then when we start to consider how this might turn into a math problem, how does that look? Okay, so let's see. Here's the information we have in the problem. A 2.5 molar sodium hydroxide solution, 25 milliliters of 5 molar hydrochloric acid solution, and the question says, what volume of sodium hydroxide? So let's read the whole thing. What volume of a 2.50 molar sodium hydroxide solution is required to titrate 25 milliliters of a 5 molar hydrochloric acid solution? So we start out with our equation, right? Here's our acid, hydrochloric acid. Here's our base, sodium hydroxide. And we know in the process of neutralization, we're going to form water. And then the whatever the leftovers are, the sodium and the chloride, we can just write it as sodium chloride. So if we go back to our flow chart, we went from volume of acid to moles of acid, using the balanced equation to go to moles of base, and then to volume of base. So that's what we had here on the right half of this chart, right? Volume of A going to volume of B. So it's similar to our approach to a theoretical yield problem, right, with these three conversions, but now we're working with molarities instead. So as we kind of follow what we're doing here, we use the molarity of the acid to interconvert between volume of acid and moles of acid. We use the balanced equation, which provides us with a 1-to-1 ratio to get moles of base. And then we flip the molarity around now to go, rather than from volume to moles, from moles to volume. Okay, so let's kind of walk through what we've got here. So we start with our 25 milliliters, which is our milliliters of acid. Then the molarity of acid we have as 5 moles per 1,000 milliliters. So we're getting out of milliliters and into moles in one step, right? Rather than writing moles per liter, we're writing moles per 1,000 milliliters. So then here it gets me to moles of acid. Then the balanced equation tells me it's a monoprotic acid and what we call a monobasic base. It says every mole of HCl is reacting with 1 mole of sodium hydroxide. That's where the balanced equation is fitting in. So now I'm in moles of base. And then the last step, I want to go to milliliters of base. So now you can see it's the molarity of the base, but it's upside down, right? Because now I want to get out of volume and go into milliliters. So I need milliliters in the denominator. So that's milliliters of base. When I do all of that multiplication, it tells me I need 50 milliliters of base to neutralize, so titrate slash neutralize 25 milliliters of 5 molar hydrochloric acid. So that's what we end up figuring out here. And remember, this still goes back to the same fundamental idea that if we're going to neutralize, it means the moles of H plus must equal the moles of OH minus. So whichever one we're adding, we need to make sure we add an amount that matches up with what we're trying to add, or what we're trying to neutralize, I should say. So this is kind of the official way to go about solving these problems. I'm going to show you a different method to solve it in a couple slides here, but this is kind of the standard, typical way that we teach how to do this. Some people like this way of kind of mimicking what they did with theoretical yield problems. Other people prefer the shorter method that I'll show you in just a little bit. So now we're going to change the problem slightly. And so the question says, what volume of a 1.42 molar sodium hydroxide solution is required to titrate or neutralize 25 milliliters of a 4.50 molar sulfuric acid solution? So again, here are my 3 pieces of information. And the question that I'm trying to answer is, what volume of base? And that's, like I said, we could either be adding base to acid or acid to base in this sort of thing. But when we think about titrate, we mean we're neutralizing. So what's different here is the acid is sulfuric acid, and that's a diprotic acid. So technically, we should then say, to get a balanced equation, I'm going to need 2 moles of sodium hydroxide, right? It's a diprotic acid with a monobasic base. So if, again, the important thing is moles H plus equals moles OH minus, then we need to make sure that works out in our problem. And then again, we make water, but 2 moles of water, and then the leftover is sodium sulfate. So we should just note 2 moles NaOH, 1 mole, well, not 1 mole, 1 mole H2SO4. So we can follow our same plan, right? Volume of acid to moles of acid, then using the balanced equation to get to moles of base, then flip the molarity over to get to volume of base. So we can follow that through. 25 milliliters of acid, I multiply by its molarity, so then milliliters acid to moles acid. Then in the second conversion, that's where we're communicating with the balanced equation, which says for every mole of H2SO4, I require 2 moles of sodium hydroxide. So milliliters acid to moles base. And then now we're in moles of base per mole of acid. And then lastly, we get to milliliters of base. So the most important thing that changed here, right, is this factor of 2 in the second step, because it's a diprotic acid and a monobasic base. So in our balanced equation, we need that 2-to-1 ratio. When we go ahead and solve this, we get 158 milliliters of the sodium hydroxide needed for the diprotic acid. So again, like I was saying, this is kind of the standard way most people approach these types of problems. I'm going to show you a shorter approach now as well, so we can take a look at that in the next one. So on the next slide, we'll do back to a monoprotic acid, monobasic base. Then we'll also consider one similar to this one that we're looking at right here. Okay, so kind of dissect things the same way. What volume of a 1.75 molar sodium hydroxide solution is required to titrate 25 milliliters of a 2.50 molar hydrochloric acid solution? So here we are as usual, right? HCl plus NaOH makes H2O plus NaCl. So simple 1-to-1 ratio that we're considering here. And so I want to go from milliliters of acid to moles acid to moles base to milliliters base. Okay, let's see if we can fit that here. I think I gave myself enough space. 25 milliliters times 2.50 moles HCl per 1,000 milliliters. So that gets us out of milliliters and into moles of acid. So that's our first step. Then the balance equation is pretty straightforward, right? 1 mole HCl is reacting with 1 mole NaOH. So now we're out of moles of acid and into moles of base. And then finally, molarity upside down, right? So 1.75 moles NaOH, 1,000 milliliters. So then cancel, left with milliliters, that looks good, and then that's our last step here. Okay, so 25 times 2.5 divided by 1,000 times 1 over 1 doesn't do anything, times 1,000 divided by 1.75. 35.7 35.7 milliliters of NaOH are required for this neutralization. Okay, so that's kind of following the method we had been using before, but I also want to show you another method. So the underlying principle again is moles of acid equal moles of base. But when I think about how I would get the moles of acid, it would be molarity of acid times volume of acid. And then if I think about how I would get the moles of base, it would be molarity of base times volume of base. So this kind of substantially simplifies our approach, but let's make a note here. This is because it's a monoprotic acid, right? Per molecule, there's one H plus being released, and it's reacting with a monobasic base. So 1 OH minus unit per molecule. And it's always for what we're doing, strong acid, strong base. But so now it starts to look a little bit more like a like a dilution problem rather than a neutralization problem. So then when I think about this, right, I can approach the problem with this equation with the understanding that my goal is to solve for the volume of base. So I can do that fairly easily, right? Just rearrange to get volume of base equals molarity acid, volume acid, divided by molarity of base. So all based on this fundamental idea that moles of acid need to equal moles of base for this titration. Okay, so let's plug in what we've got here. Molarity of acid is 2.50. Volume of acid is 25 milliliters. And the molarity of base is 1.75 molar. So unit-wise, this looks good, right? Molarity cancels with molarity, and we're left with milliliters. And so when I do that, I'm going to get 35.7 again. 35.7 milliliters sodium hydroxide. So I would say in general, teachers don't want to teach you this method right away just because it kind of results in thinking less critically about the balanced chemical reaction here. But to me, it's still relying on the most important concept in neutralization, which is that the moles of acid equal the moles of base. All that being said, right, be very aware that I made this note here to say this version of the equation, MAVA equals MBVB, that is only going to work with a monoprotic acid and a monobasic base. So in this last example, we're going to have sulfuric acid again, and we're going to do two things, right? I'm going to show you how to solve it again the standard way we showed a couple slides ago, and then also we'll kind of modify MAVA equals MBVB to fit this situation as well. Okay, what volume of a 1.50 molar sodium hydroxide solution is required to titrate 25 milliliters of a 2.00 molar sulfuric acid solution? So now what we need to be able to realize is our equation will now become sulfuric acid plus 2 sodium hydroxide, monobasic base with diprotic acid, makes 2 waters, and then the leftovers are sodium sulfate, which we're not terribly concerned with. So then, same approach, right? We can say we're going to go moles. Oh, no, sorry, not moles. We'll have to start in milliliters. Milliliters of acid to moles acid to moles base to milliliters base. And we need to have this 2 factor in mind as we do this, right? Okay, so here we go. 25 milliliters times 2 moles sulfuric acid per 1,000 milliliters. Oops. So let's see. Milliliters go with milliliters. Now we're in moles. That's the first step. Then balanced equation comes in, right? For every 1 mole H2SO4, 2 moles NaOH. Moles of acid cancel. Now I'm in moles of base. Now I flip around the molarity. 1.50 moles sodium hydroxide in 1,000 milliliters. Cancel that out, takes care of our third step, and our answer will be in milliliters here. Let's see. 25 times 2 divided by 1,000 times 2 times 1,000 divided by 1.5. 66.7 milliliters of this sodium hydroxide solution. Okay, so what about retooling our MAVA equals MBVB to fit this situation? So remember, what's true in this is that the moles H plus equal the moles OH minus. But now, with a diprotic acid, we're going to have to modify it slightly. So diprotic acid, monobasic base, rather than MAVA equals MBVB, what we need to do here is put a factor of 2 on the acid side. So because it's a diprotic acid, basically what we're doing is doubling the molarity. So I'm saying if it's 2 molar H2SO4, it's effectively 4 molar H+. This is an approximation that in second semester, if you're headed that way, you'll learn is not 100% accurate, but this is the way we approach a problem of this type. So initially this might seem counterintuitive, right? The coefficient is on the base side, so you might initially think, shouldn't the coefficient go with the base? But that's not what we're doing here. Instead, what we're saying is the effective H+ concentration is double the concentration given for the diprotic acid because it's effectively releasing 2 H+. And again, that's not 100% true, but it is the assumption that we make in this type of problem. So then if we think about the problem like that, 2 MAVA equals MBVB, again, our goal is to solve for VB, so we can rearrange the equation appropriately to get VB equals 2 MAVA over MB. And I've got all of that stuff to plug in, right? It's 2 times 2 molar, so like I said, kind of effectively doubling the molarity. Volume of acid is 25 milliliters. And then the molarity of the base is 1.50 molar. Looks good, right? Because molarity cancels molarity, and I'm left with milliliters. When I multiply all of that out, I'm going to get basically 100 in the numerator and then 1.5 down below, so 66.7 milliliters. All right, so you can do this either way. Historically, I've kind of seen students prefer to have an equation like this to use rather than walking through the entire chemical reaction each time. But it's totally up to you, whichever one you feel more comfortable with. Just make sure when you look at a problem like this, you should be asking yourself, is it a monoprotic acid, monobasic base, or is it mismatched, in which case I'd need to add a factor of 2. So it could also be the other way around, right? It could be a monoprotic acid and a dibasic base, and there I'd put the 2 with the base. If they were both diprotic, then it wouldn't matter, right? Then we wouldn't need a factor of 2 on either side because it would just work the same way in both cases. Okay, so that's it for this unit, the second set of slides for Chapter 3 and Chapter 4. So this is the end of this section, and Exam 2 will cover these 2 sets of slides. So the next video should be the Exam 2 review, and then we'll move on to Chapter 6.